Hi folks, we're going to take a look at this question that's from the class worksheet where it gives you three points which represent vertices of a parallelogram, and we need to determine all possible fourth points. Okay, now this is certainly a question I could have given you back in grade 10, and you could have maybe even grade 9 and solved it using some analytic geometry. So I would have encouraged you then to actually draw it accurately on a Cartesian plane to help you figure out the answer. Okay, but you're going to see that I'm not going to do that here. The reason being that I might end up with a similar type of problem where these 3 points are given in 3 dimensions, in which case drawing an accurate diagram just wouldn't be in the cards. So I'm going to see if I can solve this without having to rely on the Cartesian plane, and you're going to see that I'm going to use vectors to represent the sides. Okay, so first thing I'm going to do is I'm just going to represent the points A, B, and C, and I'm not going to worry about where they're placed even relative to each other. I don't care about that because I want to use the fact that parallelograms are made up of sets of parallel sides. Okay, so first of all, let me see if I can figure out how many possible answers I should be looking for. Okay, so if AC is one of my sides, well, I know I can have a parallel side somewhere here. So somewhere there, I'll call this, I'll call this P1. It's one of my possible points. Okay. Then I realize that if I take AB as one of my sides, well, here I can create another side there. So somewhere down here is going to be another point. I'll call that P2. Okay. So now the last one here, well, if I take BC as one of the sides, well, I can create another side parallel to it somewhere out here. So somewhere out here, I'm going to get what I'll call P3. And those are the only possibilities that I can get. So it looks like I can have 3 possible parallelograms. Okay. Now, since I don't know these points, I'll give them names. Okay, so I'll use X, Y to represent the unknown points. Okay, and I'll go one at a time. Now, there's a couple of things I can do here. One thing I notice, again, thinking about parallelograms, I say, well, if I take the vector AB, okay, and then I add it to the vector AC, it's going to give me the vector AP1. Okay, so that's really good. The only problem is that I'm looking for the actual point P. I'm looking for the X and Y values. So there'd be some work to do if I had the vector, AP1. How do I determine what X and Y are? So there would still be some more work to do. So I'm actually going to take a different approach. I'm going to use the fact that the vector AB, okay, and the vector CP1 not only have to be parallel, but they also have the same length. Okay, so the way I've drawn them, AB and CP1, I've drawn 2 equal vectors because they're pointing in the same direction. Got that from being parallel. Okay, notice here I'm using CP1, not P1C. I want to make sure that they point in the same direction, and because it has to be a parallelogram, they have the same magnitude. So in other words, these vectors are equal. So I have the vector AB is equal to the vector CP1. Okay, but now we'll see that we can create a very easy equation to solve. So let's figure out what the vector AB is. So remember, the vector joining 2 points, we subtract the second from the first. Okay, so we do -1 minus 2. So -3, and then here we have 5 minus -3, so 5 plus 3 is 8. Okay, and that's going to be equal to CP1. Okay, so here second minus the first, so this is going to be X minus -2, so X plus 2. Whoops, sorry, I don't want, just want a comma there, and then here we have Y minus -2, so Y plus 2. Okay. But now, in order for these 2 vectors to be the same, I need the x components to be the same. So x plus 2 has to be equal to -3. So I'm essentially solving x plus 2 equals -3. So x is -5. Okay. And then here y plus 2 has to be equal to 8. So y is just equal to 6. And so my point P1 is just equal to -5, 6. And there we go. This is how we can solve it. Okay. Now, by the way, just to let you know, it's not on purpose. It's not by accident that I chose to go from C to P1. okay, which meant I had to go from A to B because I would really like my variables to come first in my expression. Okay, so I'm going to keep that in mind when I'm setting up the other vectors here. Okay, so now let's work on this parallelogram here. So again, I want to have P2 being the second point here. Okay, so I want the vector to go in that direction. So that means I have to work with the vector BC. Okay, so similarly now I set up my equation, my equality of vectors. So I have that the vector BC has to be equal to the vector AP2. Okay, and so now let's start by calculating BC. So BC, okay, -2 minus -1, so -2 plus 1 is -1. Okay, and then here we have -2 minus 5, -7, and that's going to be equal to AP2. So again, we'll call this XY. Okay, so we've got to A, so here we've got X minus 2 in the first coordinate, and then Y minus -3, so Y plus 3. Okay, and so I know that these X components have to be the same, these Y components have to be the same. So here I know that for P2, I need my X to be equal to -1 plus 2. Notice here I'm not writing out the equation. I feel comfortable enough solving it. Okay, so -1 plus 2 is 1. Okay, and then here we have -7 minus 3, -10, and there we go. There's our second point. Now let's set up our last parallelogram. Okay, so we need this side and that side, but again, I want the P3 to come last. So I've got this vector here. I'm now going to be working with the vector CB as opposed to before I worked with BC, because I need these two vectors to be in the same direction. Okay, so I've got the vector CB, which is equal to the vector AP3. Okay, so CB now, I have to make sure I go in the right direction. So I'm going from second to first. So here we have -1 minus -2, so -1 plus 2 is 1. Okay, and then here we got the Y values, CB, so here we got 5 minus -3, so 5 plus 3 is, BC. I just realized I'm looking at the wrong one. So let's check again, CB, so -1 plus 2 is 1. Sorry about that. Okay, and then here we've got 5 minus -2. 5 plus 2 is 7. Okay, now by the way, good way to check this is since I was using CB, it should just be the opposite of BC. Okay, and we see that these two vectors are indeed opposite. Okay, at this point here, I just want to point out that these are vectors. So 1, 7 now is not representing a point, but a vector, whereas here 1, -10 is representing a point. Okay, so let's finish this off. So now we have to go AP3. So here we're just going to have X minus 2, and here Y minus -3, so Y plus 3. Okay, so my last point, P3, so the X value is going to be, I just have to add 2, 1 plus 2 is 3, and then here 7 minus 3 is 4. And there you go. There are the 3 possible fourth vertices of this parallelogram, or these parallelograms. Okay, and if you plot these on Desmos, you'll see that it does indeed give you 3 parallelograms. Okay, now what's nice about the way I set up this problem is while we didn't have the nice visual of being able to see that these points indeed help form parallelograms, this means that if I had the exact same problem in 3D, I now have a setup for it. Okay, I don't have to worry about trying to draw very complex diagrams with all these points in 3 dimensions. Okay, that's it for this one.